which I will be talking is called the Gibbs paradox. This is very important in statistical thermodynamics. So, so we got entropy is equal to Nk ln Q plus E by T. This we got before. And for this monoatomic gas system, if I put back the value of Q, I can simply write entropy as Nk ln 2 pi mkt divided by h square to the power 3 by 2 and volume plus E is 3 by 2 nkbt. So, therefore, 3 by 2 nkt divided by T. So, which is Nk ln 2 pi mkt divided by h square 3 by 2 volume plus 3 by 2 nk. This is the entropy for the monoatomic gas system. Now, as all of you know that entropy is an extensive quantity. So, what is the definition of extensive quantity? Is that if you increase the volume or number of moles of the system, the extensive property also doubles up. Whereas intensive quantity like density, it does not change. Even though you increase the volume to double, the density of the system will remain the same. And as you know, entropy S is an extensive quantity. So, if I increase the volume of the system to 2V, if I increase the number of particles of the system from n to 2n, my entropy S should reach to 2S, right. So, since entropy is an extensive quantity, let us see whether this expression of entropy, what we get for the monoatomic gas system, is holding this or it is breaking. Okay, so let us first see what happens to the energy. So, the energy of this system, let us say E prime is the new energy after we increase the number of moles, number of particles and the volume to double. So, new energy E prime would be 3 by 2, my n has now become 2n and kT. So, therefore, it has become 3 by 2 n kT cross 2. So, 2E. So, E was my total energy before and E prime is my next new energy after I made the system double. So, this is valid that energy is also an extensive quantity. So, this quantity has doubled up when I increase the volume and the mole. What happens to the entropy? So, let us say S prime is my new entropy after I increase the volume and the particle number. So, then my it was so it has become 2n number of particles, 2n kT ln we have 2 pi mkt h square 3 by 2. My volume also has now become 2V plus 3 by 2. here particle again become 2n and k. So if I take 2 out, so I get to nk ln 2 pi mkt h square 3 by 2 volume plus 3 by 2 nk. Not just that, we also get another term as 2 nk ln 2 from this expression, because here we have 2v and here we have 2n. So, this 2 we have brought out of this bracket, but because we have 2 here, so we got ln 2. So, we got 2 nk ln 2 here. So, if you look at this term, this is nothing but my previous entropy S. So, now my new entropy S prime is actually 2s, not just 2s, but it also has an extra term 2 nk 2 nk ln 2. So, my S prime, instead of becoming just 2s, it also has an extra term, and this is called the Gibbs paradox. So, before, what's the meaning of Gibbs paradox? Is that before Gibbs pointed this out, whatever expressions we had used for q and mainly q, the partition function, was based on that definition of q. And when Gibbs pointed this out, that entropy, which is an extensive quantity, is not fulfilling this even for a simple monoatomic gas. So, then scientists had to think that the definition of q has some problem. And what could be the origin? The origin, if you remember, we basically started from the definition of thermodynamic probability W. We started from thermodynamic probability definition W is equal to n factorial divided by n1 factorial, n2 factorial, n3 factorial. So, Gibbs said that there is a problem in that definition of thermodynamic probability, and the problem is, as you remember, thermodynamic probability basically gives a number of microstates. So, Gibbs said that there is a problem in counting the number of microstates. We are basically overcounting. And how we are overcounting? We are overcounting by assuming the particles are distinguishable. If you recall that definition of thermodynamic probability W, n factorial divided by n1 factorial, n2 factorial, n3 factorial, and so on and so forth, it was fulfilling the particular macrostate, and it was giving the right number of microstate for each macrostate. And to get that, we assumed that particles are distinguishable, but in practice, particles in a quantum system or in a classical system, they are completely indistinguishable. And there is the problem Gibbs pointed out, that since particles are not distinguishable, we overcounted them, and because of that overcounting, there was a problem in the definition of q, and that is where we get this this paradox that entropy is not showing as an extensive property. So, we have to now find out the actual, the correct definition of thermodynamic probability W, which we will see next.